Okay, ji, Bismillahirrahmanirrahim. Okay, we can resume our session now. Okay, it's about 9:53. So, so we finished discussing the tension members. Any question from the portion of tension member we have discussed in the first part of this lecture? Any question from your side? Is there any questions? Okay, I assume that there are no questions and all the things you have understood completely. Okay, now we will go to our lecture number 6. Okay, okay, let me okay, now we are going to discuss the compression members. Okay, we finished discussing the tension member, and this compression member we will discuss some parts or some portion of this lecture we will discuss in the remaining time. Okay, and the leftover portion we will discuss in the makeup class. Okay, so the contents we are going to address in the compression member is that we will have some introduction, what we call compression members, what are the different types of compression members. We will go through the buckling mode, so the column theory. We will see that what we call critical buckling stress, what we call critical buckling load, and what is the meant by effective length, and what are the various requirements for the design and analysis of compression members based on AISC. Okay, then in the remaining or in the makeup class we will discuss the local stability, we will discuss the AISC tables, so column design. Okay, then we will have more discussion on effective length, and we will also discuss the effective length in case of inelastic columns. So in short, what are the compression members in steel structure? Compression members are those steel structural members which are subjected to only axial compressive forces. Similar to the tension members, they are the members which are subjected to axial compressive stresses. Okay, and loads are, there is no eccentricity between the centroid and the load. Okay, the load is concentric. It means that load is applied at the centroid of the cross section. Okay, and the compressive stresses in the compression members can be estimated using the simple formulation, which is this formulation. You can calculate the compression stresses by the load divided by the area. Okay, so, and these stresses are assumed to be uniformly distributed across the cross section. Okay, now this, as we discussed, that the compression members are the members which are subjected to axial compressive forces, and axial compressive forces mean that the load is concentric. Okay, concentric, they are not eccentric. Okay, it means that there is no bending moment involved, or there is no bending moment that is produced by these axial load if the load is applied concentrically. But bending moment in compression members is regarded as the secondary effect. Okay, and they are usually neglected. Okay, because the loads are considered concentric, they are not considered eccentric. Okay, but we have another type of member that we call beam column. Okay, if you have axial load which is acting on the member, and at the same time you have some lateral load which is acting on the member. For example, there is a column which is exposed to wind load, so this member we call beam column. Okay, column we have bending moment. Okay, so we will consider the bending moment once if we are dealing with, or we are analyzing or designing a beam column. But if we are talking about pure compression member, they do not have the bending moment. Okay, so bending moments, for example, is included in the beam columns. Okay, so where we can find these compression members, so you can find them in multi-story buildings, you can find them as a bracing member. So they bracing members can be tension members, they can be compression members. So you can see in this figure, the elements which are highlighted by the red color are the compression members, and you can see that you can find them elevator tanks, you can find them in trusses. Trusses, you know that we have tension members, we have compression members. Okay, in arches we also have compression. In the case of cable stayed bridges, the towers are the compression members. Okay, then we have another terminology we call tie and stud. Okay, the inclined members which are subjected to the axial tension and axial compression, they are known as the stud and tie. Okay, this is called stud and this is called tie. Okay, strut and tie. Okay, so you can find them in trusses, like if this is a truss and this member will be subjected to compression. Okay, the forces that will be developed in that will develop in this member will be the compressive forces. Similarly, this case, if you have this loading and this member, so the compressive forces or compressive stresses will be generated in this member. Similarly, if this is a truss, so in this member you have the compressive stresses. So point of explaining that these members in trusses, you have a tension combination, compressive member combination. So when you are designing any truss member, so you should know the theory or the back end calculation of tension and compressive members, so that you are able to design both tension and compression member. If you know how to design a tension member and if you know how to design a compression member, so you will be able to design a truss, steel structure truss. Okay, so some of the terminologies which we will use in the compression member, so they are listed on this slide. So you can see that the moment of inertia. Okay, we have parallel axis theorem. Like if you have you remember from your engineering mechanics, if you want to calculate the moment of inertia at the centroid, so one will be the major axis and the second will be the minor axis. Okay, if this is not a rectangle, okay, or square, otherwise both will have the same. So if it is a square, so the both axes will have the same moment of inertia. Okay, so one of the axis we call major axis. Okay, and the second axis on which the moment of inertia is minimum, so we call it minor axis. So if we want to transform this moment of inertia to any axis, so we use parallel axis theorem. We know we use radius of gyration. Okay, which is the square root ratio of moment of inertia and cross sectional area. Then we have effective length. Okay, effective length means this is a member, compression member, the end condition effects. But if the end condition are fixed, so these due to this end conditions, you will have effect on the deflected shape of the member. So this will be about 0.5 L if this is the total length. Okay, so this is due to this end condition. And if we have the same member which is pinned, okay, if this is pinned, so in this case you will have deflection in the full length, and we will say that K in this case is equal to 1 and K in this case is equal to 0.5. Okay, so end condition also affect the deflected shape or deformation in the compression member. So similar to the tension member, we have slenderness ratio, but in this case, in the tension member, we were having a slenderness ratio. But we denoted slenderness ratio in tension member using this notation. But in case of compression member, we will designate the slenderness ratio using this. Okay, there's an additional term K. Okay, we will there is another thing we call critical loading. Critical loading is that load at which buckling occurs. Okay, like for example, you have a member and which is subjected to axial compressive loading. Okay, for example, the load is 1 kip. Okay, first, then you move on to 2 kip, you move on to 3 kip. Okay, Now this is representing the magnitude of the P, okay? So at 1 kip, you will not have any buckling or deformation in the member. At 2 kip, you will not have any, but if you keep on increasing the load, so for example, at, you can say the 10 kip, so there will be deformation in the member. So that load, that P load is called axial load, we call critical load, okay? Critical load is that load which causes buckling, or beyond which there will be buckling in the member, or the member fails by stability, not by the yielding in the compression, okay? So this is the difference between the what we call a critical load, okay? Then we have the compressive strength, CR, so we will see what is that in the coming slides, okay? So this is about column theories. When we are discussing compression members, please remember that there are two type of columns or compression members, or we will stick to the column theory. There are two type of column in steel structure. We call them cylinder column and we call them stocky column, okay? Cylinder columns are those columns which the cross-sectional area is very less, okay, very small, and they fail in stability, okay? They fail in stability means there is buckling. They failure by buckling, okay? Stockier column are small columns, okay? So these columns, the failure is by yielding material, yielding of material. Yielding, you can say that, or fracture, you can say, okay? So they do not fail by buckling, okay? Failure by yielding, fracture, etc., okay? So the column which fail by buckling, we call cylinder columns, okay? And the columns which fail in the yielding, we call the stocky column. And cylinder columns are more in length as compared to the stocky columns, okay? So this is the two type of columns, okay? So we will deal these two type of columns, design and analysis in compression member, okay? Is that clear to all of you? What is a stocky column and what is a cylinder column?
Yes, sir.
अच्छा, दो किस्म के columns होते हैं. Cylinder columns, the columns which fail by buckling, we call them cylinder columns, okay? Buckling, cylinder. If they fail by yielding, compression yielding, we call them stocky columns. And this is an example of stocky column. This is stocky column, this is a cylinder column, okay? So as I told you that if you see that if there are two type of columns, one column has is cylinder, okay, the cross-sectional dimension is very less, and if you apply the same magnitude of the load on these two columns, so this column will fail by buckling and this will not fail, okay, by buckling. And if you keep on increasing the load, maybe it fail by yielding, okay? So this, the column which fail in buckling, we call cylinder column, and the column which fail in yielding and etc., we call stocky column. And as we discussed that there is a condition or K value, we see that the end condition value, okay, this K value stands, take a value 1 unity for a case of pin connected members, okay? Now this is that K value, okay, for pin connected members, okay? Let me write it down here. Pin connection, pinned end connections, okay? The K value will be 1, okay? So if you keep on, as we discussed that if we keep on increasing the load, okay, like we apply a load here, there is this is a cylinder column and it does not fail in buckling, so that load will not be called as critical load, okay? So the load which causes instability or buckling in cylinder column, we call it critical load, okay? And this column produces the different buckling modes. Okay, like if you keep on increasing the load, so the buckling modes will be changing in the member. Okay, some member will fail in this deformed shape, some member will fail in this deformed shape. Okay, so there are different buckling modes as well. Okay, now the point is how we can estimate the magnitude of critical load. And the critical load is the load which causes buckling in the cylinder column. And this buckling or the critical load we can estimate by a formula which is known as Euler formula. Okay, this Euler formula is a function of modulus of elasticity and the length of the member. And if we replace here this I with this AR square, so this equation will take a form this one. Okay, so we can say that the critical load, okay, is proportional to the slenderness ratio of the column, and that slenderness ratio we refer to it as L by R. Okay, if the length is more, the critical load will be less. Okay, if the length is high, if the length is less, the critical load will be higher. Okay, so there is an inverse relation between the critical load and the length of the member. Okay, and it is important to note that the critical load you can estimate using this Euler load formula. Okay, this is given by this formulation. So as I discussed that the critical load or the load which causes failure of cylinder member is called critical load. Okay, you can see that critical load is the load at which or beyond which buckling occurs in the member. Okay, so you can see there is a steel member, so if you keep on increasing the axial load, so it is failed in stability. Similarly, these are the pictures of reinforced concrete columns, so which have failed in stability. Okay, by buckling. Okay, failure by buckling. This is also failure by buckling. In other words, you can say that the axial load acting on this member is either equal to or greater than critical load. Okay, now we will go through an example like how we can calculate or how we can know that my column is failing. Okay, we can check that whether my failure is going to take place in my compression member we can check that using this simple formulation. Okay, so this is example 4.1. It states that there is a wide flange section. Okay, this is a wide flange section. Depth is 12 inches and the weight of this section is 50 pounds per square inch, I guess. So 50 pounds per square feet, yes. So this is used as a column to support an axial compressive load of 145 kips. The acting load on this member, this is applied concentrically. This is 145 kip. Okay, and the length of the member is 12 feet. So the ends are pinned. Okay, without regard to the load or resistance factor, investigate this member for stability. Okay, and it is further stated that the grade of the steel need not to be known because the critical load is not a function of any yield stresses or any fracture stresses. Okay, so what we have to do, that we have to go to the manual and we have to check that what is the radius of gyration. So as we discussed that there are there will be two values of this radius of gyration. So, and you have to select the minimum value out of these two values. So if you go to your manual and you go to that chapter number 1, and if you will find that for wide flange section, this section, the R value is 1.96 inches. Okay, and first, you know, the formulation of critical load. The formulation of critical load is given by this formula. So there is E, there is A. So you also need to know the A value. This radius of gyration and this cross-sectional area for this member, you have to find it from the manual. कोई बता सकता है कि मैनुअल में कौन से चैप्टर से हमें ये मिलेगा, ये क्रॉस सेक्शनल एरिया और ये मिनिमम रेडियस ऑफ गायरेशन?
फर्स्ट चैप्टर।
वो आपने वो कौन सा पेज था, पेज नंबर याद है किसी को? भी बताया भी था पेज नंबर चैप्टर 1
47 सर।
47 में आपके पास यू विल हैव डिटेल ऑफ एंगल, लेकिन अब आप यू स्क्रॉल इट डाउन एंड अप दैट चैप्टर, so you will also find cross sectional properties of wide flange section. Okay, from where there you can find the cross sectional area, this area. So you should simply plug in the values, E value is fixed, A value we can have it from the manual. The radius of gyration we already have it, the length is given, length is 20 feet. Okay, now when you calculate the critical load, this load, it comes out to be 279 kPa. Okay, now you have to compare this value with this value. Now the value, the load which is acting on the member is 145 kPa, and the critical load at which the buckling starts, or at which the buckling occurs, is about 280 kPa. It means that you do not have any instability in your member due to this load. Okay, because the load acting on this member is 145 kPa and the critical load is 279 kPa. So this value is less than 150, where the load acting on the member is, sorry, this should be the right sign. So this is higher than the applied load, so it means that the column is stable, and it will remain stable, and the overall factor of safety against the buckling in this member for this condition is 1.92. Okay, so this is not a function of any compressive or any tensile or any fracture or yielding stresses. Okay, it depends upon the geometrical properties. Okay, ठीक है? Is that clear to all of you?
Yes sir.
Oh, okay, now let's go through it. What is this? Now consider a long cylinder compression member shown in figure 4.4a. Okay, where is 4.a? This is 4.a. Consider a cylinder column. Okay, cylinder column means that there will be, this column will fail in by buckling. Okay, this is stating if the axial load is slowly applied on the member, it will ultimately become large enough to cause the member to become unstable and assume the shape indicated by the, dashed line. What are those dashed lines? These are the dashed lines. If you keep on increasing this load, okay, so there will be an instant that this member will start buckling. Okay, so this member will, this will be the failure of the member. Okay, what else it's saying? The member is to have the member is said to have buckled, and the corresponding load is called critical buckling load. This PCR is called critical load buckling, which we can estimate with the Euler formula. Okay, this is the first case. If the member is stockier, as shown in figure 4.1b, this one, this is 4.b, a larger load will be required to bring the member to the point of instability. Okay, it is saying that the magnitude of the critical load or the failure load will be higher for stockier column as compared to the cylinder column. Okay, for extremely stocky members, failure may occur by compressive yielding rather than buckling. It is saying that if the member is उससे भी छोटा हो, stockier हो, so it will not fail in by buckling, it will fail by yielding. Okay. Prior to the failure, the compressive stresses PA by A will be uniformly over the cross section at any point along the length, whether the failure is by yielding or by buckling. As I told you, the compressive stresses before the failure, if it is failing by buckling, is it a buckling, is it a cylinder member or is it a stockier member? The stresses are uniformly distributed over the cross section, and this stresses magnitude you can estimate with this formulation. The load at which buckling occurs is a function of cylinderness. And what is their cylinderness? We know that critical load is equal to pi I A. This is cylinderness. Okay, as we discussed. Okay, now the load at which buckling occurs is a function of cylinderness, and for very cylinder member, this load could be very small. It means that you have two members, cylinder members. One is of this length and one is of this length. Okay, this length. So for this, the critical load will be higher. This is, let's say, 1 and this is 2. So the magnitude of PCR1 will be greater than PCR2. If the member is very cylinder, so the magnitude at which it starts buckling or it fails in stability will be very less. Okay. If the member is so cylinder that stress is just before buckling is below the proportional limit, that is, the member is still elastic and the critical buckling load is given by this formulation. Okay, in this equation, E is the modulus of elasticity. You guys are familiar with these terminologies. L is the length of the member between the points of support. Okay, it means that if your member is very cylinder, if your member, compression member, is very cylinder, so what will happen that the stresses, if we have, this is, I think, stress or strain, and this is, I think, strain, and this is the behavior of the steel. Okay, up to here you have proportional limit. Okay. For cylinder column, the critical stress or the stresses for cylinder columns, stresses that will be generated in the member are elastic. Okay, they remain within the elastic range. Are elastic. Okay, yeah. For cylinder columns, and for stockier column, the stresses will be in the inelastic range. Okay. समझ आई आपको? Is that clear to all of you that for cylinder columns stresses are elastic, or they remain within the elastic range? Is that clear to all of you?
Yes, sir.
Okay, आप लोग भी थक गए, मैं भी बोल बोल के थक गया. Okay, next up is the derivation of this Euler formula. Okay, next up is the derivation of this Euler formula. What is Euler formula? This critical load, pi E I by L square. So now we will go through the derivation of this critical load or the Euler formula, which you use to estimate the critical load. Okay. So if you have this type of member, this is an horizontal member. Let me draw it here. I know you guys will be tired. मैं भी थक गया. बात भी नहीं कर सक रहा मैं, लेकिन चले. If this is a member which is subjected to a critical load like this, okay, and this is 0 here, and x is the distance from this point, any distance, and L is the length. Okay, this is you can say point A, x is 0, this is say point B, this is pinned, this is pinned. Okay, now the deflection that will occur in this member is given by this formulation. Okay, and if you replace this equation with different notation, if you you represent by this double dot, and you bring this to the right hand left hand side, so the right hand side will become 0, and this value will be this whole value, I'm sorry, MEI. Okay, but M is equal to bending moment into Y. Y is the deflection. If you replace this variable with this, so this will take this form. This will become a homogeneous differential equation. And from your fourth semester or third semester, you know how to solve a second order differential equation. The solution to a second order differential equation is of this form. Okay, in this, okay, the C takes the value, C is this. C is, I think, if you go to this equation, C is the magnitude of, I think, PCR by EI divided by its coefficient. This is 1. So this comes from the knowledge of differential equation. So you have this solution now. You have C value, but you do not know the A and B values. So we have to use conditions to find the value of A and B. So the first boundary condition is that at point A, x is equal to 0. If you put this value in this equation, x0, so this will become 1 and this will become 0. So you will get a value A is equal to 0. Similarly, if you use the second boundary condition, the second boundary condition is at x is equal to L. We have that if you put the y value is 0, okay, because there is no deflection here, there is no deflection here. Y value here is 0, y value is still 0 here, okay. So if you put this value, so it will give you an equation that this whole term is equal to 0. It means that either b is 0 or either this term is 0. So we consider that this term is equal to 0. So sine 0 means that it can take a value of 0. It can take a pi, 2 pi, 3 pi, n pi, any value of sine. Any value of sine is 0. Okay. Means 0, pi, 2 pi, 3 pi is 0. So, so we know that CL is equal to n pi. We can take this value. CL is equal to n pi. And we know the value of C. C value is this much. So if CL, so we can equate it to PCR by EI into L. N pi. Okay. Now what you do, you take the square root at the both sides. So you will end up with this formulation. Okay. N is the number of modes. Okay. If it is buckling mode is 1, this will take a value of 1 for this type of mode. Okay. If you have this one, key number is khatam. Okay, now this has been explained on this slide. So n values, if n value is 1, if n value is 0, so there is no buckling, the critical load will be 0. If there is 1, so there will be buckling load. Okay, so accordingly you can see that what are the different buckling modes that can occur in a compression member. So if you put the A and B value to that equation, Y equation, so this equation will give you this solution. Okay, and if you go for this one, we have already seen that we get this derivation. Okay, we went up to this point. Okay, if you put n is equal to 1. Okay, similarly you can say that in this formulation, A is the cross-sectional area, R is the radius of gyration. Okay, and LR we call the slenderness ratio, is the measure of the member slenderness. Okay, if the critical load is divided by cross-sectional area, critical buckling stress is obtained. Okay, if you know this formula, you know the critical load, you divide it by the cross-sectional area. So these stresses you will get in your member, we call it critical stresses. Okay, okay. Now this same thing, area will be cancelled out. Okay, so I will this is the last slide. Okay, now for design or analysis of the column, so you can see that the stresses, if the stresses in the members are plotted against the slenderness ratio, so you will get this type of curve. Okay, so this is the same equation. Okay, Euler equation, this equation, and this is valid up to the elastic point or elastic limit or the proportional limit. And you know that the stresses that remain within the proportional or elastic limits are cylinder elements. Okay, cylinder columns, you can say, because the stresses are elastic. Okay, if the stresses after the elastic range, you can approximate it with the same equation, but you should replace the E value. In the elastic range, the E value is constant. But once you go to the inelastic range, the E value keeps on changing. Tangent, E tangent. You just have to replace the E with the tangent modulus. Okay. So this is representing the stocky column behavior. This is representing the cylinder column behavior. Okay. But in order to know that which the stresses are elastic or inelastic in your member, you need to know the cylinderness ratio. You first have to compute the cylinderness ratio. You have to plot it here, and you have to see that where your point is located. If it is located here, you have to use this formulation to compute the critical stresses. If it is here, you have to use this one. So you guys should think about it, and from onwards we will continue in the makeup class. Okay, you can think about it for 5 minutes. If you have any question, you can ask me. Okay. Any questions?
No, sir.
Okay. Is the CR in the class now? CR है class में कोई?
No, sir.
अच्छा, फ्राइडे के दिन हम फिर मेकअप क्लास लेंगे, ठीक है, इंशाल्लाह।
Okay, sir.
चले, ठीक है। तो आप लोगों को कुछ समझ आई थोड़ी बहुत?
Yes, sir. Alhamdulillah.
ठीक है, चलें। आप लोग अगर जाना चाहते हैं तो ठीक है, बट आई विल बी स्टेइंग इन द क्लास अप टू 10:45। अगर किसी का क्वेश्चन हो तो पूछ सकते हैं, ठीक?
Allah Hafiz, sir.
अल्लाह हाफिज।